All right, so today we're going deep, deep into the mind of Jeff Hawkins.
Tech visionary brain enthusiast.
I like that brain enthusiast.
Yeah,
He
yeah,
really is.
yeah.
So we're talking about his 2 books, On Intelligence and 1,000 Brains.
Really fascinating stuff.
And he's known for the PalmPilot.
Right? Like way back.
Yeah, I mean, this guy is a serious tech innovator.
Yeah.
But his real passion is the brain and how it works. And he actually thinks that the key to building truly intelligent machines is understanding how our brains work.
Yeah, that's his thesis.
Okay, so let's talk about why he thinks that.
Yeah.
What's wrong with the traditional approach to AI? Like we've got ChatGPT, we've got all this other amazing stuff going on. What's the problem?
So I think the best way to understand his criticism is through this thought experiment called the Chinese room.
Okay.
So have you heard of this before?
I have.
Okay, so imagine you have this room.
Right.
And inside the room is a person who speaks absolutely no Chinese.
Okay.
They're given a giant rule book. And through a slot in the door, people are feeding Chinese characters.
Okay.
And based on the rule book, they're able to manipulate these characters and send responses back out.
Right.
Now, to an outside observer, it would appear that the person in the room
Understands Chinese.
understands Chinese.
Yeah, you're right.
But do they?
No.
No. And this is Hawkins's point that a lot of AI is simply mimicking
Behavior.
Yeah.
Without actual understanding.
Exactly.
Okay, so he's saying that the way that we've traditionally approached AI is kind of like the Chinese room, where it looks like there's intelligence there, but there really isn't.
It's just mimicking, yeah.
Okay, so then the next question is, well, what is intelligence then?
Right.
And where does it come from? What does Hawkins say about that?
Well, he thinks that the key to unlocking intelligence lies in the neocortex.
The neocortex.
Yeah.
Okay, and that's the outer layer of the brain.
The wrinkly part.
Okay. So what's so special about the neocortex?
Well, Hawkins proposes that the neocortex acts like a prediction machine.
A prediction machine?
Yeah, essentially, it's constantly building this model of the world based on sensory input and then using that model to anticipate what's going to happen next.
Like all the time?
All the time.
So my brain is like predicting the future?
Yeah. Well, in a
all the time?
Constantly. Constantly. Okay.
Like it's happening right now as you're listening to
it. What is it going to say? Are you predicting what I'm going to say?
Maybe.
That's a little creepy, but...
Okay. But it's happening all the time.
Yeah.
Like think about how you recognize a friend's face.
Right.
You can recognize them even with different lighting from different angles, even with different hairstyle.
Yeah.
So your brain is making predictions about what their face should look like.
Right.
And then adjusting to the variations.
Oh, okay. That makes sense.
It's really quite remarkable when you think about it.
It is, but I'm also kind of freaked out now because I'm like hyper aware of my brain. But it's all subconscious.
We're dictating things.
You know, we're not thinking about it actively.
Okay, good.
It's just, you know, this amazing ability of the brain to anticipate, so.
But so you said the neocortex is the part of the brain that does all this predicting. So what's so special about that part of the brain as opposed to the rest of the brain?
Yeah, well, Hawkins argues that the neocortex is incredibly uniform in its structure.
Okay.
Whether it's processing vision or sound or touch or language.
It's all basically doing the same thing.
Yeah, and that suggests that there's a single underlying algorithm governing its operations.
Okay.
And this is where his theory of invariant representations comes in.
All right, so you're throwing a lot of big words at me.
I know.
Invariant representations, what are those?
So think about how you can recognize a dog. Whether you see it from the front, the side, or the back, whether you hear it bark or growl.
Yeah.
It's still a dog.
It's a dog.
Your brain has created this stable representation of dog. That's invariant to those variations in sensory input.
Okay. Okay, that's kind of blowing my mind a little bit.
Yeah, it is.
Like, it's still a dog even if I only see its butt.
Exactly.
Okay, that's...
Or a tail.
Yeah, all right.
Your brain knows it's a dog.
All right, so these invariant representations are basically like these stable concepts that our brain creates so that we can recognize things regardless of how we're sensing them.
Precisely, precisely. And these invariant representations are crucial for how our neocortex builds this predictive model of the world.
Okay, I'm starting to get it.
Yeah.
But I have one more question.
Okay.
How can our brain make accurate predictions when the world is, you know, constantly changing?
That's where memory comes in.
Okay.
The neocortex doesn't just store these abstract patterns. It also stores very specific details from our experiences.
Right.
And it's constantly weaving these invariant representations together with very specific memories to make predictions in a given context.
So could you give me an example?
Sure. So imagine a man back in the 1890s.
Okay.
He's waiting for his wife's train to arrive.
Oh.
Now, he knows that her train always comes in 4 hours after the eastbound train leaves.
Okay.
But the exact time varies.
Right.
So he needs both the invariant structure,
the
4-hour delay, and the specific detail of when the eastbound train left.
To know when to meet his wife.
Exactly.
Okay, that's a really good example.
That's how our neocortex works.
Okay.
It combines general knowledge with specific details to anticipate what's coming next.
So my brain is basically a time-traveling supercomputer.
Well, you know, in a sense...
That's pretty cool.
It is amazing. The power of the brain is something we take for granted.
Absolutely. Absolutely. So I think we've covered a lot of ground here just in this first part of our deep dive.
Yeah, we have.
And I'm ready to go even deeper.
Well, we've got a lot more to talk about.
I'm excited.
Me too.
Let's do it.
Okay.
So we're back. And we're really getting into the nitty-gritty of how our brains work.
Yeah, this stuff is pretty mind-bending.
It is. I mean, we left off talking about how the neocortex is like a prediction machine.
Right. Always trying to anticipate what's coming next.
But I'm still grappling with this idea, like, how much of what I perceive as reality is actually just my brain's prediction?
Well, it's not that we're living in some kind of simulated reality, like in the Matrix.
Okay, good, because that was my next question.
But our brains are definitely playing an active role in shaping how we experience the world.
So it's not just our senses passively taking in information.
No, it's more like our neocortex is constantly interpreting that information.
Using its model of the world.
Exactly. It's comparing the incoming sensory data to its predictions and trying to make sense of it all.
So it's like my brain is telling me a story about the world based on what it expects to happen.
That's a good analogy. And most of the time, the story flows smoothly because our predictions are pretty accurate.
But what about when they're not accurate?
That's when we get things like optical illusions or misinterpretations.
So like when I see something that's not really there, or I misjudge a situation.
Exactly. Your brain is trying to reconcile its predictions with the sensory input, and sometimes it gets it wrong.
Our brains aren't perfect prediction machines.
No, they're not. And that's partly because our brains are incredibly complex.
Billions of neurons, right?
Trillions, actually. And all those neurons are interacting in intricate ways that we're only beginning to understand.
So it's not just about having the right information. It's about how that information is processed.
Precisely. And that processing can be influenced by a lot of factors, like our emotions, our past experiences, even our current state of mind.
So even with all this amazing predictive power, our brains are still prone to biases and errors.
Yes, definitely. And sometimes our brains prioritize speed over accuracy, especially in situations where a quick decision is crucial for survival.
Like, if I'm walking down a dark street and I hear a noise, my brain might jump to the conclusion that it's danger, even if it's just a cat.
Exactly.
Yeah.
Better to be safe than sorry, as they say.
Right. So this predictive power is amazing, but it's not foolproof.
No, it's not. But it's still one of the most remarkable things about the human brain.
It is.
Yeah.
And it makes you wonder, if we're building intelligent machines based on this model, how do we account for these potential biases and errors?
That's one of the biggest challenges in AI research right now. How do we ensure that these machines are making decisions based on logic and reason, not just on faulty predictions or biased data?
It's like we don't want to create machines that inherit all of our human flaws.
Exactly.
Right?
We want them to be better than us, in a sense.
Yeah.
More rational, more objective.
But also, hopefully, still capable of things like empathy and compassion.
Right. Those are important qualities, too.
It's a tricky balance. But I guess that's what makes this whole field so fascinating, right? The potential is huge, but so are the risks.
Absolutely. And it's why it's so important to have these conversations, to really think critically about what we're creating and how it might impact the world.
Okay, so we've talked about the neocortex, we've talked about prediction, we've talked about biases and errors. But there's one more big idea from Hawkins that I want to dive into. The 1,000 brains theory.
Oh, yeah, that's a good one.
I mean, is he literally saying that our brain is made up of 1,000 little brains?
Not literally, but it's a good way to visualize it. Hawkins argues that our neocortex isn't just one big unified structure.
Okay.
It's more like a collection of thousands of smaller, specialized modules.
Like a team of experts, each with their own area of knowledge.
That's a great analogy. And just like a team, these modules communicate and collaborate to solve problems and make sense of the world.
So it's not like there's one central me in my brain calling all the shots.
Not exactly. It's more like a distributed system, where different modules are responsible for different tasks.
Like one module for recognizing faces, one for understanding language, one for planning my day.
Exactly. And these modules are constantly sharing information and voting on the best course of action.
Voting. Like a democracy in my head.
In a sense, yes. The modules with the most accurate predictions or the most relevant information have the most influence.
So it's not about having one all-powerful brain. It's about having a lot of smaller brains working together.
That's the idea. And Hawkins believes that this distributed approach is what makes our brains so adaptable and resilient.
Okay, I'm starting to see the appeal of this theory. It explains why I can be good at some things and terrible at others. Maybe some of my modules are just better trained than others.
That's a possibility. But it also highlights the importance of learning and experience. The more we expose our brains to new information and challenges, the better these modules become.
So it's not just about having a lot of brains, it's about training those brains.
Exactly. And that's where Hawkins's work has implications for education and child development. If we want to raise intelligent kids, we need to provide them with rich, stimulating environments that allow all those modules to flourish.
So it's not just about cramming their heads full of facts. It's about giving them opportunities to explore, to experiment, to learn through experience.
Precisely. And that's something to keep in mind as we develop artificial intelligence as well. If we want to create truly intelligent machines, we need to think beyond just programming them with information. We need to give them the ability to learn and adapt through interaction with the world, just like we do.
So we need to move beyond this idea of a single, all-knowing AI and embrace the power of distributed intelligence.
Exactly. It's a more nuanced and ultimately more powerful approach to creating truly intelligent systems.
Okay, I'm really starting to see how Hawkins's ideas could revolutionize the way we think about intelligence, both human and artificial.
It's a paradigm shift, really. And it all starts with understanding the incredible complexity and power of the human brain.
Which is why this deep dive has been so fascinating. We're learning so much about ourselves and about the potential of intelligence itself.
It is fascinating, and we're just getting started. There's so much more to explore.
Well, then let's keep going. I'm ready for part 3. Okay, so we're back for the final part of our deep dive into Jeff Hawkins and his quest to understand intelligence.
And we're going to tackle a topic that might seem a little surprising at first.
Okay, hit me with it.
Movement.
Movement. Like physical movement.
Exactly.
I mean, yeah, we move around, but what does that have to do with intelligence?
Well, Hawkins argues that movement is not just an output of intelligence.
Great.
Like our brains telling our bodies to do something.
Right.
He sees it as also an input, a crucial part of how we learn and think.
So it's not just that intelligent beings move.
Right.
It's that the act of moving actually helps us become intelligent.
Exactly. He points out that even maybes, their earliest learning experiences involve movement.
Yeah, they're always grabbing things, putting stuff in their mouths.
Yeah, reaching, grasping, crawling.
They're like little explorers.
Exactly. And all those interactions provide feedback to the brain that helps refine its model of the world.
So it's like they're not just seeing a toy. They're picking it up. They're feeling it. They're shaking it.
Yeah, they're figuring out.
And that's how they're learning about it.
Exactly. It's all about active engagement.
Okay.
Not just passive observation.
So movement is kind of like a feedback loop that helps our brains learn and adapt.
Exactly. And this applies not just to physical movement, but also to what we might call mental movement.
Mental movement.
Yeah, the way we explore ideas and concepts in our minds.
Okay, I think I get it. Like, when I'm trying to solve a problem, I might mentally try out different solutions.
Yeah, you're kind of moving through the problem space in your mind.
Exactly, like I'm visualizing different possibilities.
That's a great example.
And trying to see what works.
And that mental movement isn't random.
Right.
It's guided by those reference frames.
Right, those mental maps that we talked about.
Exactly. So movement, both physical and mental, is really at the heart of intelligence.
It's like our brains are embodied. They exist in the real world.
Yes.
And they learn through interaction with that world.
That's a key point. And it has big implications for how we think about AI.
Okay, how so?
Well, if we want to build truly intelligent machines,
Yeah.
machines that can learn and adapt the way we do, maybe we need to give them bodies.
Whoa, You're talking about robots.
Yeah, robots that can experience the world through movement.
And learn from those experiences.
Exactly. This is actually a really hot area of research right now.
Oh, really?
Yeah, it's called embodied AI.
Embodied AI, I like that.
And it's all about building robots that can interact with the physical world.
Interesting.
And learn from those interactions.
So instead of just programming a robot with a bunch of rules,
right,
we let it loose in the world.
Yeah, let it experiment.
And figure things out on its own.
Exactly. And that's how it can develop a deeper understanding of how the world works.
That's pretty cool.
Yep.
So Hawkins is basically saying that the future of AI might involve a lot more robots.
Yeah, potentially.
And a lot less sitting around thinking.
It might be a lot more active.
Yeah, more hands-on, literally.
Exactly. It's about getting out there and experiencing the world.
Okay, I'm starting to get really excited about the future of AI now.
Me too. It's an exciting time to be alive.
It is, and I think Hawkins is really pushing the boundaries of what we thought was possible.
Absolutely. He's a true visionary.
So, to kind of wrap things up,
yeah,
what do you think is the most important takeaway from Hawkins' work? Like, if someone is listening to this and they're like, okay, I get it, the brain is amazing, AI is cool, but what does it all mean?
That's a great question. I think the most important takeaway is that intelligence isn't this mysterious, magical quality.
Okay.
It's a product of very specific structures and processes in the brain.
Right. It's not just about being born smart.
Exactly. And that means that intelligence can be understood.
Okay.
It can be studied.
Yeah.
And it can be replicated.
And maybe even enhanced.
Exactly.
Which is a pretty mind-blowing thought.
It is, and it's empowering.
Yeah, it is. It means that we all have the potential to be more intelligent.
Absolutely.
If we understand how our brains work and how to train them.
And if we can build machines that can learn and adapt to the way we do.
Yeah, the possibilities are really endless.
They are.
Well, I think we've officially reached the end of our deep dive.
We have. We've covered a lot of ground.
But I feel like we've only just scratched the surface of this topic.
There's always more to learn.
Always more to learn. So to our listeners, if you want to dive even deeper into this, definitely check out Jeff Hawkins' books on intelligence and 1,000 Brains.
Highly recommend them.
They'll really make you think differently about how your brain works, how the world works, and what the future might hold.
Absolutely. And thanks for joining us on this journey.
Yeah, it's been a pleasure exploring these ideas with you.
Likewise. Until next time.
Keep those brains buzzing.